Okay, dear students, now let's see how we can also solve question number 1 of this workout part. The question says, show that the set containing 1, x, and x plus x squared is a basis of a vector space over a set of polynomial functions with degree less than or equal to 2 under the operations of addition and multiplication of the field of set of real numbers. So we are now going to see how we can show this W as a base of the vector space of the given set. So let's proceed. So as you know, the set given here is non-empty because as you see there are 3 elements here, so it is non-empty, and it is also a subset of polynomial functions with degree less than or equal to 2, because if you see all the elements here, you see their degrees are less than or equal to 2. Now let's assure the following two conditions in order to show the betas. One is the case of linear independentness, and the second one is the case of a spanning condition. So let's now see how these elements are linearly independent. So let's take arbitrary 3 scalar numbers or real numbers a, b, and c. Now let's try to write as these functions as a linear combinations. So we directly multiply 1 by a, and b by x, and c by x plus x squared. And let's equate this with 0 function 0 here. Now here, if we are able to obtain at least one non-zero value for a, b, and c, we can say that these 3 functions are linearly independent. But if we are unable to obtain such non-zero value so that this can be true, you see this set is considered to be made of linearly independent elements. So let's see how we can do that. So as you see, a times 1 makes a, and b times x makes bx, c times x is cx, and then cx squared equals 0 can come. So in order to have 0 here, necessarily the coefficient of x squared and the coefficient of x as well as the constant must be 0. So directly we can have the constant a here 0, and here the coefficient of x is b plus c, and this b plus c must be 0 because the coefficient of x to the right side is 0, and here also the coefficient of x squared, which actually is c, must be 0 because we don't have here x squared, so it is accepted as the coefficient is 0 for the right side. So c is 0. So if a is 0 and c is 0, clearly b plus c is 0. Since c is once 0, b goes to 0. So as you see, this happens if and only if a is 0, b is 0, as well as c is 0. This shows you that this set is made of linearly independent functions, and because of this we can understand that W is a set of linear independent elements. But this by itself is not enough. We have to show again the spanning condition of this set, that is to say that for any arbitrary element from the given one, from a polynomial function with degree less than or equal to 2, let's see how the element can be formed by the linear combination of these 3 elements. Okay, so this set must generate any function whose degree less than or equal to 2. And because of this, let's have again, let's check the spanning condition and take an arbitrary quadratic expression, ax squared plus bx plus c, where capital A, B, and C are real numbers. Now take arbitrary scalar numbers a, b, and c. So our intention is to construct or to generate this quadratic equation from the given set using these scalar numbers. So let's now rewrite the combination of these scalar numbers with the given elements of W. So as you see, or as you saw before, this is a times 1 plus b times x plus c into x plus x squared. This must make ax squared plus bx plus c. Now we are checking whether the given quadratic expression or a degree 1 expression, because in case a is 0 it will be a linear one, and if a and b are 0 you can have a certain degree 0 expression, and if c is 0, a and b are also 0, we can have a 0 function. So our intention here is whether this set of elements can make this quadratic equation or not. We are going to check that one. So here we are having a times 1 b times x plus c into x plus x squared. So our intention here is to write a, b, c. This is small letters a, b, c in terms of these capital letters a, b, and c, because this is a quadratic expression. We took one element from the vector space. Now we are running to see how this vector space element can be generated by these three elements of W. So let's proceed now. This, after simplification, we can have a plus b plus cx squared is equal to x squared plus bx plus c, because as you see b and c, we can have bx plus cx, so you may take b plus c as a common one, and then x is taken out, so we are having now this. So for this, c must be a, b plus c must be b, and this small letter a must be c. So clearly a is c, and b plus c must be b, and c must be a. So please try to know that this is a capital letter C. Now from this we can understand that a is small letter a is a, and b is b minus a, and c is a. So as we are having here, c is a, as you see. Since c is a, look, we are having a here, so small letter a is again capital A, and b is nothing but it is b minus c, but we know what c is, it is a, so it will be b minus a. Now we have written these small letters a, b, c in terms of capital letters, as you see, a, b minus a, and a. For example, if you are having a certain quadratic equation made of 2x squared 3x plus 4, having a2, b3, and c4, capital C4, then these values a, b, c, small letters a, b, c, can be known from this, you see. So as we said, we took a to be number 2, so a, you can take small letter a to be 2, and small letter b is going to be 3 minus 2, and this is going to be 2 again. So in such a way, you see, the quadratic equation you took can be generated by this set of elements. So this shows you that this set can generate any function whose degree is less than or equal to 2. Because of this, we can say that this set which is called W is a basis for the given vector space. I hope you have understood. Now coming to the next one, we have question number 2 for the workout part. So you are asked to find the limit of this one. So in order to find the limit of this, let me call this to be y. Y is equal to 3 the power of x plus 4 the power of x the power of 1 over x. And from this, let me introduce ln both sides, because we are having an exponent 1 over x. So ln y is equal to ln of 3 the power of x plus 4 the power of x the power of 1 over x. So using the logarithm property, this 1 over x can come in front, and then we can have ln y is equal to ln of 3 the power of x plus 4 the power of x over x. Now let's have this limit. As you see, the limit of ln y as x goes to infinity is the same as the limit of the expression here as x goes to infinity, but students know that as x goes to infinity, 3 the power of x plus 4 the power of x, this goes to infinity, and ln of this large number again goes to infinity. Again we are having here infinity because x is running to be infinity. So this sort of limit is indeterminate type of infinity over infinity. So we can have now L'Hopital's rule for this, as you studied before. So applying a L'Hopital's rule, you can obtain this to be like this. So the limit of ln y as x goes to infinity is equal to the limit of ln of 3 to the power of x plus 4 to the power of x over x. Now just apply L'Hopital's rule, try to derivate the upper one. So the derivative of ln of 3 to the power of x plus 4 to the power of x is 3 to the power of x ln 3 plus 4 to the power of x ln 4. 1 over 3 is the power of x plus 4 to the power of x, and when you derivate the inner one you will get the numerator expression, and as you are derivating x it will be 1, so you will never see 1 here, but it is there. Now as x goes to infinity can come. Now in order to evaluate this in a better sense, let's multiply the numerator and the denominator by 1 over 4 to the power of x, because that one is the larger exponential expression compared to 3 to the power of x. So try to multiply the numerator as well as the denominator by 1 over 4 to the power of x. So you can have this condition, and as you are doing this, look, you can have this one, 3 to the power of x over 4 to the power of x. You can write as like this, and ln 3 comes here. Now look here, 4 to the power of x can be cancelled by 4 to the power of x, ln 4 can come, and here again 1 over 4 to the power of x can cancel this one, and you do have 1 here, and then 3 over 4x. Now look, as x goes to infinity, this approaches to 0. 0 times ln 3 is 0, then ln 4 can come, and again as x goes to infinity, this goes to 0. 0 plus 1 is 1. So finally you will obtain this to be ln 4. This is not the answer actually. We are interested to find the limit of y, not ln y, right? So there should be a mechanism of writing y from ln y, and for that you need to recall this. Y is the power of ln y, as you know, and from this you can have now the limit of the question we are having now turns to be the limit of y as x goes to infinity, because we have said that this is y, and this is going to be the same as e the power of limit of ln y as x goes to infinity, because e the power of ln y is y, and this is e the power of, now we have determined this limit over here, it is obtained to be ln 4, so e the power of ln 4 and e the power of ln 4 makes 4. So the answer for this is going to be number 4. And next from this we have the other question, and question number 3, you are asked to find the interval of n for which this improper integral can be convergent and divergent. This can be done in the following manner. This is the integral from 1 to infinity of 1 over x to the power of n dx. This is equivalent to this one, just making x to the power of n up. And from this, limit can undergo as b goes to infinity, because in place of this infinity we can have b here. So using power rule, this is going to be the limit of x to the power of 1 minus n. You simply add 1 here on the exponent, and 1 minus 1 from 1 to b, and now substitute b in 1 by 1 in place of x. As you see, this is going to be the limit of, put b in x, b the power of 1 minus n, minus, put 1 in x, 1 the power of n expression is 1, so we are right, minus 1 over 1 minus n. So you can take 1 over n minus 1 as a common out, because analysis is done on b. So look, 1 over n minus 1 is taken out, and then the limit of minus 1 as b goes to infinity is minus 1. So we are having now plus of limit of b the power of 1 minus n. So for this to be convergent, necessarily 1 minus n should be, as you see, less than 0, because it converges to 0 if this is negative. So if 1 minus n is less than 0, that is to say n greater than 1, or 1 to infinity, the improper integral is going to be convergent. Otherwise, if for instance you are having 1 minus n to be positive or equal to 0, it will be divergent. The reason is, you see, if 1 minus n is positive, if this is positive, b is positive, the power of positive goes to infinity, and because of this sake the series is the improper integral will be divergent, and so the intervals are this.